Hi, my name is John Bors and I'm a firmware applications engineer supporting the SmartRate product line at Microchip. In this video, you will be introduced to dynamic channel multiplexing. This new feature in the Microchip SAS 4 controllers and expanders enables efficient link aggregation using a dynamic form of time division multiplexing. The need for this technology arises due to the connection-oriented nature of the SAS protocol. An open connection between an initiator and a target owns the resulting physical pathway for the lifetime of the connection, blocking other traffic while that connection is open. A better mechanism would be to allow multiple devices to share the same physical pathway, thereby increasing overall bandwidth and reducing latency. This problem has been addressed using the following technologies which have their own limitations: rate matching, time division multiplexing, and edge buffering. Let's examine each to understand the value that DCM provides. Rate matching is defined in the SAS standard specification. Rate matching is performed by interleaving deletable primitives on a higher rate connection to match the bandwidth available at a lower rate device. This wastes a significant portion of the bandwidth provided by the shared pathway. SAS 2 introduced a time division multiplexing scheme that allowed an initiator to support two independent connections on the same physical pathway. SAS 2 multiplexing was unpopular because it was inflexible. It really only provided benefit when all targets in the system operated at half the initiator link rate. Sas Edge Buffering is a link speed aggregation solution that uses a virtual target initiator pair with a RAM buffer implemented at each target attached expander PHY. The expander then acts as a proxy for the initiator-target relationship by using a store and forward mechanism. The effectiveness of this solution is limited because buffering efficiency varies for different block sizes, buffered targets can be starved in mixed buffered-unbuffered topologies, increased latency for small block sizes due to data store and forward. Error recovery requires significant expander processing, new expander code and qualification for some new HDD SSDs. Buffering is only supported to direct attached targets and not to JBODs, and only data from one target is transferred on one PHY at a time. DCM is a time division multiplexing technique which overcomes these limitations. Let's look at this solution in more detail. 4 independent transport and link layers are implemented in the initiator for every physical PHY. A multiplexing PHY layer is implemented in the initiator and in each expander PHY. Each multiplexed physical PHY then fans out to 4 logical link layers in the expander. The expander connection manager and crossbar switch functions are increased in size to accommodate 4 times the connection pathways from each multiplexed PHY. And lastly, flow control buffers are implemented to prevent overflowing connection pathways with slight and/or temporary bandwidth mismatches in the connection pathways. SPL packets from each logical channel are interleaved onto the physical channel using a weighted round-robin scheme. The channel weights are determined by the connection rate of each logical channel. In this example, each DCM logical channel is carrying a 6 gigabit per second connection, so the channel weight for each channel is 1. This means that one data packet is transmitted from each channel before the pattern repeats. This example shows two 6 gigabit per second connections combined with one 12 gigabit per second connection on the same DCM link. So in this case, while the 6 gigabit per second channels are transmitted once, the 12 gigabit per second channel is transmitted twice before the sequence repeats. The benefits of this design include dynamically expanding the number of channels serviced per PHY, dynamically allocating PHY bandwidth on a per connection basis, interleaving multiple connections to increase PHY utilization to near 100%, eliminating unfairness bandwidth starvation effects of SAS SATA buffering, and eliminating the store forward needs of SAS SATA buffering. Bench test results provide a quantitative confirmation of the advantage of DCM. In this video, we examined the rationale for effectively sharing a physical SAS link between an initiator and an expander, reviewed historical mechanisms to deal with it, and provided an overview of DCM as a superior solution that meets this need.